Hello, this is Lazarus at Telecom Tech, where telecom and networking technologies are simply explained. Today, we'll be simply responding to questions you asked about BGP. In a video a few weeks ago, I asked you to share with me in the comments any questions you may have about BGP that haven't been clearly answered in my BGP playlist. This video is the response to those questions. I've separated the video into chapters so you can quickly go to the section of the video that addresses the question that you're most interested in. Alternatively, you can watch the whole video and gain even more understanding from the inner workings of BGP. As always, if you like my work so far and you found this and other videos useful, don't forget to subscribe and to activate notifications to be informed when new content is published. User Afaksha7229 asked two very good questions. The first is, what are the key parameters to consider if asked to design BGP for a network? How is it done and what are the requirements? Now this is a really big question and you can probably create a whole series of videos to answer it. Even so, I will examine this at a very high level. Now concerning design, we must remember the purpose of BGP. BGP is a path vector routing protocol, and thus its purpose is to route traffic between autonomous systems. So this 30.30.30.0/24 network, which exists within AS140, is advertised within that AS using iBGP. And these two routers then advertise the network to their eBGP peers. This is then propagated throughout the network, and once it reaches those routers within AS100, they're informed of a specific list of ASs, which is the AS path, which shows them how to get to that intended destination network. Now, having that in mind, the first design principle you should take into account is the design of the autonomous systems themselves. IGPs are used within each AS, and BGP is then used to advertise those networks inside each AS to the external ASs. So you should always consider, how many ASs will you create? Are you going to create one AS or multiple ASs? That depends on the size of your network, the geographic dispersion of your network, as well as the logical separation of entities within your network. All those things are things you must think about when designing. Next, you have to think about the fact that you are interconnecting with other network entities, like ISPs and possibly other enterprise networks. You will be sharing information about your AS with those other entities and vice versa. When you interconnect with other BGP networks, you will typically make some kind of contract or agreement concerning the types of attributes that are shared and advertised, and even how and if you're allowed to modify those attributes. Next, you should consider redundancy and high availability. In BGP, this is achieved using redundant eBGP peerings, redundant links, using loopbacks as your BGP source, as well as BGP multipath and additional paths. All features that allow BGP to be robust and introduce redundancy into the network. Now, all of these should be part of your design since BGP is used in large networks where extremely high availability is absolutely vital. Security is another issue that you should keep in mind as well as part of your BGP design. I won't go into detail about that here because there's another question later on that addresses specifically security. Now, this question of BGP design is indeed a deep one, but hopefully this small overview should give you an idea of the types of things you should consider. Now, Afaksha7229 asked the second question concerning BGP security and asks, how do we implement security in BGP other than using the more traditional methods of TTL security? Also, SRB 1855 asks about security, specifically referring to a PKI infrastructure for BGP. Now, it's interesting here that while BGP is critical for the functioning of the global internet, BGP was not originally designed with security in mind. This lack of inherent security features has led to several vulnerabilities and attacks over the years. So to understand the methods of mitigating security issues with BGP, it's important to understand the kinds of vulnerabilities that BGP has. So here is a breakdown of the key security concerns associated with BGP, and immediately after, I'll talk about the methods used to mitigate them. One particular security concern is prefix hijacking. Now, this occurs when an AS incorrectly advertises IP prefixes that it does not own. This can lead to traffic being misrouted, intercepted, or dropped, causing service disruptions and potentially allowing malicious activities such as man-in-the-middle attacks. Now imagine AS190 here begins to advertise the 30.30.30.0/24 network as its own. This would divert traffic from this user here to AS190 rather than to the correct AS140. Route leaking is another issue that we have to take into account. It's something similar to prefix hijacking, but it happens for a different reason. A route leak happens when a BGP router incorrectly advertises routes learned from one peer to another peer, violating intended routing policies. For example, AS100 here may be configured to inform its customer about the 30.30.30.0/24 network. But because of some misconfiguration, AS100 leaks these routes to AS150 as well. So AS150 now thinks that it can reach the 30.30.30.0/24 network destination via two paths, via both AS100 as well as via AS140, resulting in suboptimal routing and even routing loops. Another security concern is called BGP session hijacking. Now, in this scenario, an attacker may intercept or hijack a BGP session between two routers, masquerading as the legitimate BGP peer, potentially injecting malicious routes or disrupting legitimate routes. This can result in traffic interception or denial of service. For example, here an attacker may break into the communication channel between these two BGP peers and may itself become peers with one or both of these routers, thus manipulating and injecting routes into both of these routers. Now, there are other threats as well, but this gives you an idea of the kinds of things that can happen. Now, how do we mitigate against these potential attacks? There are several best practices that we should deploy, and these include things like prefix filtering. Prefix filtering essentially creates a filter to ensure that only authorized prefixes are advertised and accepted. For example, AS100 here knows which prefixes AS190 is allowed to advertise. So it creates filters here that will filter out any prefixes that are outside of these predefined allowed lists. Now, which prefixes will be filtered is typically a result of an agreement that the administrators of these two ASs create between them. So if AS190 tries to advertise the 30.30.30.0/24 network to AS100, AS100 will filter out that route and will remain safe. This helps mitigate against prefix hijacking by limiting what routes are allowed to be shared between BGP peers. Another feature is route validation. Now, this is used to validate the origin of BGP routes to ensure that they are coming from the correct and valid ASs. This can be done using techniques like resource public key infrastructure. Now, RPKI associates a cryptographic signature with the IP address blocks and the AS numbers that are being advertised, allowing BGP routers to verify the legitimacy of route announcements. Now, another very important part of BGP security is BGP monitoring. Now, this is a huge area of expertise, and there are whole companies that have been created to deal with just this very specific need. BGP monitoring tools can be used to detect anomalies in routing behavior, such as unexpected changes in routing paths or the appearance of new prefixes. There are a whole multitude of tools that can monitor BGP routes in real time, providing alerts for suspicious activities. Early detection using monitoring can mitigate the impact of security breaches. And then we also have BGP session authentication. Now, this allows you to secure BGP sessions between BGP peers using MD5 or stronger cryptographic authentication methods. This helps to prevent session hijacking and tampering. Now, another approach that is also helpful in securing BGP is making sure your network design includes network segmentation. Now, BGP routers should be isolated from general purpose networks, and they should use out-of-band management and apply access controls to minimize exposure to attacks. Now, often in BGP labs, students wonder, why can't I ping the BGP router from my end device? And actually, you don't need to. It's unnecessary. And in production networks, you would never have an end device communicate directly with a BGP router. The BGP routers are there just to advertise the routes, and they shouldn't be directly reachable from the networks they advertise. So even though BGP was originally designed with a lack of built-in security mechanisms, many tools and methods and techniques such as prefix filtering, route validation, RPKI, session authentication, and robust monitoring network operations can significantly enhance security of a BGP infrastructure. Ongoing vigilance and adaptation to emerging threats are also crucial to maintaining a secure BGP environment. Now, the next question comes from these two users, and they're asking for some more information about redistribution into BGP from IGPs, as well as suggesting that we examine various ways to redistribute a default route using BGP. Now, the role of redistribution for BGP is an important one. Within each AS, we have routes that we need to inject into BGP so that they can be advertised beyond the local AS. These can be advertised in one of two ways, either by using the network command under the BGP configuration mode, or by redistributing into BGP. Now, to redistribute routes into BGP, we typically enter into the BGP configuration mode on a Cisco router and issue the redistribute command. Now, this context-sensitive help of the redistribute command on a Cisco iOS router, you can see all of the options that are available for redistribution. Now, don't worry about the syntax of this command for now. The point of what I'm showing you here is that you can see the various sources from which you can redistribute routes. And these sources include connected routes, static routes, as well as various dynamic routing protocols. Now remember, by default, redistribution is a global affair. In other words, when you choose one of these sources, it means that all of the routes from those sources will be redistributed. For example, if you configure redistribution from EIGRP, then all EIGRP routes within the local router will be injected into BGP. If you choose redistribute connected, all connected routes on the local router will be redistributed. However, keep in mind that you can use a route map to filter out what you want to redistribute and what not. But I won't go into that now. We'll talk about route maps shortly in another question. Now, how do you redistribute a default route? Well, there are several options. The first thing you can do is redistribute a static default route, along with all other configured static routes, using the redistribute static command, like so. This, of course, will work only if you already have a static default route configured on the router itself. Alternatively, if you don't want to use redistribution, you can use the network 0.0.0.0 mask 255.255.255.255 command, which essentially tells the local router to advertise the default route that's in the routing table to all of its BGP neighbors. Now, this, of course, again, assumes that a default route exists within the routing table. Now, that default route may be statically assigned, it may be learned from an IGP, it doesn't really matter. If that default route is in the routing table, it will be advertised. If it's not, the router will simply not advertise anything in BGP. Now, this, of course, is not redistribution, but this is injecting a route directly into BGP from the local device. Now, there's a third option as well, and you can use the default originate keyword in the neighbor command like so. Now, in this case, you will cause the local router to advertise itself as the default route to that specific neighbor, regardless of whether or not you actually have a default route configured in your local router. Now, let me just note here that whether you choose redistribution or the use of the network command will also affect the BGP attributes associated with that injected route. The origin attribute, which I describe in detail in another video, and you can find the link to that video in the description below, shows that an origin attribute of I, or iGP, is given to those routes injected using the network command, and an origin attribute of incomplete, which is specified by the question mark, is given to those routes injected using redistribution. Now, when applying the BGP best path algorithm, if you have two or more routes where all previous attributes are tied, the iGP origin, or I, is preferred over the incomplete or question mark origin. Take a look at the origin attribute video for more info about that. For now, I can say that you can see that for the 30.30.30.0/24 network, which was advertised using the network command in one case and the redistribution command in another, you can see that the attribute with the I origin is chosen as the best path. Now, which method you will use to advertise the default route, or any route for that matter, that will depend upon your requirements and your network topology. Now, Demand Red LFC 4180 has requested a discussion about route maps and BGP, and how and when to use route maps. Now, this is actually an interesting one because route maps are used very often to manipulate what networks are shared between BGP peers. Route maps are constructs that can be configured within routers to very granularly filter out specific routes. They can also be used to modify any of the BGP attributes of specific routes. Now, how are route maps applied? Well, take a look at this topology here. In this example, we have a route map called filter configured on R4. And this route map is applied in an outgoing direction to its neighbor 2.2.2.2, which is router R2. The result of this configuration is that any BGP updates sent from R4 to R2, that is, in an outbound direction, will have the policies of the filter route map applied to those BGP updates. Now, what kind of route map policies can you have? Route maps can perform a whole series of policy modifications. They can filter specific routes so that routes advertised by one router will be filtered out of the update before it's sent on to its BGP neighbor. They can also change BGP attributes. They can change the weight or the med or the local preference or other attributes to affect how the BGP neighbor will calculate the BGP best path algorithm. And you can even modify the AS path, for example, associated with particular routes. Now, route maps can be applied in an inbound or outbound direction, and understanding what that means is especially important. For example, applying them in an outbound direction from the point of view of R4 means that you are modifying attributes or filtering routes before you send out the update to its neighbor. That way you are affecting how the other router will perceive the BGP topology. Similarly, applying them in an inbound direction makes the changes, like filtering routes, BGP attribute modifications, and so on, before the update is received and processed to be included in the local BGP table. Now imagine that we are applying route maps on this pair of iBGP peers. Let's say that this is an interface between two different ISPs. You can send out your BGP updates with outbound route maps modifying various attributes in an attempt to make the other ISP's BGP processes behave in a particular way. Similarly, the other ISP can try to do the same thing to you. But remember, you can always change any modifications that may have been made by applying route maps in an inbound direction on all BGP updates you receive from your neighbor. In any case, this whole example makes the case that you should always ensure that you agree with your counterpart in the other ISP on the types of attributes that you can change and which you should not. Trying to change BGP attributes on your outgoing BGP updates in an attempt to make your neighboring ISP behave in a particular way is often considered a hostile act. In other words, you're trying to force the BGP processes of your neighbor to function in a specific way. But that's often perceived as being hostile. So you always have to make sure that there is some sort of agreement in the kinds of things you're allowed and not allowed to do. Now, one more thing I'd like to add before I end off with route maps is that the inbound and outbound directions are often confused with inbound and outbound directions of user data. Remember, the route maps act upon BGP updates. They act upon control plane data, not the user data itself. And understanding this will resolve much confusion. Now, Zuavi6391 has suggested that we take a look at peer groups. And this is actually a very good topic that I didn't cover at all in my BGP playlist. And I may actually cover it in a future BGP video when I revisit that list. Now, one thing that you will quickly realize when working with BGP is that you need to manually configure all of the BGP peers. This is in contrast to protocols like OSPF and eIGRP, which automatically detect and create adjacencies. This makes BGP much more administratively demanding. However, there are tools that make configuration easier, and peer groups are one of those tools. When you're configuring BGP, you'll actually often find that some of your BGP neighbors need exactly the same settings. Now, typing out those same commands over and over for each neighbor can become pretty tedious. Also, when BGP prepares updates, it does so separately for each neighbor, resulting in exactly the same update being sent to multiple peers, which can really eat up your CPU resources. Now, with peer groups, you can bundle those neighbors together and apply all of your configurations to the group in one go. This not only simplifies your setup, but also reduces the number of updates BGP has to generate. So instead of your router burning through CPU cycles to prepare and send identical updates for each individual neighbor, it can now prepare one update for the entire peer group. Take a look at this topology here. We're configuring the same MED and the same iBGP multi-hop parameters with all three neighbors of R1. Without peer groups configured, the BGP configuration of R1 looks like this. Now you can see that all of these parameters are triplicated for the routers. For each individual peer, we have to configure the update source command, we have to configure the iBGP multi-hop command, and we also have to apply a route map which changes the MED of those particular routes. Now, with peer groups configured, the configuration looks like this. Now, these commands here are used to create the peer group. Once the peer group is created, then you can apply BGP parameters to the peer group as a whole. And this is what is done here. As you can see, the update source, iBGP multi-hop, and route map commands are only applied once each. And R1 here only needs to generate a single BGP update, and it sends it to all three routers that belong to that peer group. Now imagine that you have 20 or 50 such routers. You can very clearly see how easily this scales up with the same configurations sent to all devices. Now, Vijayanthiv273 has expressed an interest in seeing how BGP can be used in conjunction with tunneling mechanisms to help keep particular IPs hidden and to make routing easier. Now, BGP itself is not a tunneling protocol, but it can be used in conjunction with tunneling mechanisms to achieve the goal of hiding or abstracting certain details of network infrastructure. Some tunneling technologies that leverage BGP for this purpose include MPLS, Layer 3 VPNs, and VXLAN. Here's a brief description of each. Now, MPLS Layer 3 VPNs use BGP to distribute VPN routes. The data itself is tunneled through the network using MPLS labels. The combination of BGP and MPLS enables the separation of customer traffic, which essentially hides the customer IPs, and allows complex routing policies to be simplified at the customer edge. Now, in scenarios where MPLS and BGP are applied, BGP distributes VPN routes using the route distinguisher and the route target mechanisms, which ensure separation between different VPNs. Now, another tunneling technology that uses BGP is VXLAN, and it uses MPBGP EVPN as its underlay network. Now, this is often used in data centers and cloud environments to provide layer 2 and layer 3 services across a virtualized environment. It actually abstracts network details, creating what we may call VXLAN tunnels, and hides IPs and allows for scalable network designs. You can find out more about this at my VXLAN series of videos. Now, while BGP itself is not a tunneling protocol, it is extensively used in conjunction with tunneling techniques such as MPLS and VXLAN, as well as with GRE and IPsec, to achieve goals similar to those you described in your question. Now, finally, we've come to our last question, which comes from RSK066, and they ask why we need iBGP since we can use an IGP and redistribute external BGP routes into our network. Well, actually, that's a very good question. Now, this is a question that's often asked and is one of the difficult parts of learning about BGP. The logic behind the architecture of BGP is that BGP is used to advertise routes from within an AS to regions that are outside of the AS. Now, let's take a closer look at this topology. You can theoretically use an IGP to redistribute all of the internal networks within AS 140, including the 30.30.30.0/24 network, into this single eBGP router, which in turn will advertise those routes to its eBGP neighbor and beyond. However, if we do this, it restricts the injection of routes to that single router. This has several disadvantages, including having a single point of failure. Now, by using iBGP within your AS, you can collect the various routes from multiple locations of this whole AS and inform this eBGP router via iBGP of all of the routes that exist within that autonomous system. Now, this solution is more distributed, it's more reliable, and it's a more efficient way of collecting all of the routes within the AS to be advertised outside of this AS. And if you consider that many ASs have dozens or even hundreds of routers, it would not be very scalable to use that internal IGP to redistribute those routes into this eBGP router simply to have them advertised beyond. Now, in addition, by using iBGP, you can already change some of the BGP attributes of those routes that are being collected within the AS. So from the very moment that those routes are injected into BGP, those attributes can be modified as you see fit. And when they're advertised to this edge router, that edge router will then share those routes with those BGP attributes modified with the rest of the ASs in the topology. So using iBGP within the AS is a much more scalable, robust, reliable, and efficient solution. So that's it. Thanks so much to all of you who contributed your questions and made this video a success, and hopefully it made it useful to you and to the general telecom and networking community. As always, if you do like this video, please click the thumbs up button. And if you'd like me to address other related topics, feel free to let me know in the comments below. And please subscribe to get updates of newly published videos. I'm Lazarus at Telecom Tech. I hope this has been helpful for you, and I'd like to thank you for watching.